Oh, the pleasure is mine, Dennis. Thank you very much for the introduction, and thank you for having me here again at the Virtual Pipeline Summit. I feel very lucky to be a part of this. I'm sure pipeliners everywhere will agree that the VPS series has been extremely well run, so a big thank you to you and the team at ITEP, and of course Sabrina and Ruben running the production. We have 3 presentations as part of this technical session. Each will be around 15 minutes long, followed by a 5-minute opportunity for you, the audience, to engage with the speakers. Please type your questions and comments in the web platform, and I will pose them to the presenters on your behalf. With that, it's time for me to introduce our first presentation.
Okay, Danny, thank you for that introduction. And I'm very happy to be here today for Baker Hughes to present on our topic of dry pipeline pre-commissioning. My name's Pete Dixon. I'm an engineering manager with the Process and Pipeline Services Division of Baker Hughes. I've been with them for about 18 years now, specializing in deep water pipeline pre-commissioning. So the topic we want to go through here today is some new developments we have had and we're seeing more of in the industry, where we're looking at new ways to pre-commission large gas export pipelines with reduced amount of resources and reducing the carbon footprint for those activities. So before I spend time developing the new techniques, I just want to take the time to pause and go over the existing or traditional techniques of what we do in pre-commissioning. And by pre-commissioning itself, I mean the step between the pipeline fabrication, the installation and construction, where there's a handover from the installer of the pipeline to the owner of that asset. So Baker Hughes are operating in the service space between the installer and the eventual owner operator, where we're proving the integrity, the bore and the strength of that pipeline before it's handed over for hydrocarbon use. So the traditional sequence is what I'm showing on screen here, which is from left to right. We're filling the pipeline with water, usually chemically treated seawater. We're running pigs in the line to clean and assess the bore. So we'd have gauge plates on those pigs to assess the bore. And then a key part of it would be the hydrotest or strength test, where we pressurize up the water within that pipeline and demonstrate that it's leak-free. And then we can offer an optional inline inspection survey or caliper survey, where we're looking for dents or ovalities within the bore of the pipeline. So we do a baseline for the owner. And then potentially the hardest part of the operation for a large export line would be then dewatering the line. So all that seawater would pumped in and pressurized. We then need to depressurize and push out with air or nitrogen. So that would be where the main horsepower, where the biggest spread of equipment would be that dewatering phase. And then removing the moisture from the line. If it's a gas line, we need to get it very dry. So we would usually be blowing dry air, super dry air through the line, and then finishing that up with a nitrogen purge and pressure pack to get the line ready for hydrocarbon introduction. So where that's an export line, that's usually beach to beach, so from shore to shore through potentially deep water. So 2,000 to 3,000 meters deep is where Baker Hughes have done a lot of our work. So it's a huge amount of equipment, a huge amount of horsepower to do this, and a lot of water and diesel would be involved in that operation. So ways to streamline this, make it more efficient, make it cheaper, make it safer, is something that we're always striving to do and develop within the industry. So what gives us the headroom to do this? So we work and our clients work under the guidance of DNV, so the Norwegian Standards Agency, who are broadly dictating what certification and methods we need to go through to sign off these new pipeline systems as ready for hydrocarbon. So within their main governing standard, they have a waiver for that hydrotest. So there's certain circumstances where we don't have to do the hydrotest. So where the disadvantages of that pressure test are extraordinary, we can achieve the same level of confidence in the line by other means. And those other means are typically the mill test. So as the pipe spools, the individual pipe spools before they're welded together to make the pipeline are made, they're individually strength tested. And then from that point on, their storage and cleanliness and makeup into the pipeline are more rigorously inspected and signed off at each step. And then by design, the standards and the factors of safety involved in the system creation are at a higher level than they would be conventionally. So this is something where it's attractive to our clients, and we're seeing it more and more in the industry, where 500 plus kilometer lines through 2,000 meter deeps, this becomes a much more economically attractive way of doing it, as well as a quicker way of doing it. And at the end there, I'm saying that the main pre-commissioning activity that we then do to hand it over to the client is the cleaning and the gauging. So assessing the bore of the pipeline are still activities that Baker Hughes would need to do. So as a side-by-side comparison of the conventional versus the new pre-commissioning, the first three steps, the filling, testing, dewatering, are what we're trying to eliminate here. So the column on the far right is the new technique that's still under development. It's been done only a couple of times in the industry, but we miss those steps completely. So we're missing weeks, if not months from the schedule. We take that out and we start with the drying and conditioning of the line, and then move on to the inerting phase, which is the same for both. So overall, on this example line where we're over 500 kilometers, maybe nearly 1,000 kilometers a line, we can go something like 54 days, so maybe 2 months faster, or at 38% of the schedule, with commensurate savings on equipment, savings on diesel, but also savings on how well we can predict the schedule of it. So without air drying the line, because we haven't put water in the line, we save on the uncertainty of that drying phase. We know exactly how long this process will take end to end, which is a big bonus for our clients. So the pigging train that we still need to do, as I said, we still need to condition the line, clean the line, and gauge it. So we can end up with a pig train, something like on the screen here. So we would still have an air pack. So we pack the pipeline to a certain pressure before introducing any pigs or fluids. And then the fluid slugs in there are monoethylene glycol, which is used to inhibit the water in the line and keep it as a liquid and stop it forming hydrates. And that's always run in a nitrogen blanket to stop it becoming a flammable mist mixture. So the nitrogen's there as an inert gas to avoid any combustible events. And then we're splitting up the pig train to split up the mass of the meg, so it's not all in one location while we're pigging. We're putting in enough meg to condition and clean the line, and then follow that up with a caliper if required at the end. So this is a much trickier operation to engineer when it's dry, when there's not a full volume of liquid in the line, when we only have gas ahead of the pigging train. So we use flow assurance modeling for software like Olga we've used in the past, or Baker Hughes in-house toolbox calculator, where we're modeling the pipeline profile, the bends, the uphills, downhills, any features where there's a T or a valve, the masses of the pigs, the masses of the meg, and then the injection and pressure at the flow rate of the nitrogen as it goes in and comes out. And we're doing that to balance the speed of the operation against the speed excursions of the pig itself. So there's a lot of engineering goes in at this stage, at the feed stage, before we get to the proper pre-commissioning model itself. So an example of the challenge we've got there is the red line that I'm showing on this graph here is the pipeline profile, where we have a very steep, very prolonged downslope down to 2,000 meters water depth. And we're trying to get the pig train that we saw, where we have a mixture of the pigs themselves and the liquid slugs are going to go down the hill with an amount of air or nitrogen ahead of them, but it's not enough to stop the pigs speeding away completely. So what we're doing is balancing the pack pressure. So what I've shown on screen here is the 18 bar pack pressure. Is trying to balance the mass of the pig train as it comes down the hill versus the flow rate that we're injecting at that point. And while it's a protracted process, we can spend months in this engineering phase going through iterations of this. To me, this is the real key of the operation, designing the pig train from an early stage so that we get a workable solution, so that the equipment spread and the schedule when we get to site is well understood and well optimized. Because what we're trying to do is minimize those speed excursions, so that meg slug between the pigs stays between the pigs and we don't lose containment of the meg, because it still needs to clean and it still needs to condition the pipeline. So what we end up with on site, although I said it's a much reduced spread, and it is, we have very few fluid pumps, no hydrotesting pumps, no real brake tanks here. It still ends up being quite a big spread. So I'll take you through what we have on there. So we're always limited on site with how much equipment we can fit on. We're dealing with heat, we're dealing with noise. So the main footprint on here is the air compressors. So we start in this case with 34 air compressors that are providing 30,000 standard cubic feet per minute of air, which is still a lot of air despite the low pressure application at 24 bar. Feeding that to the dryers, which are going to knock out pretty much all the moisture. Then the dryers feed it to the nitrogen membrane units, which Baker Hughes can run at normally 95% purity. So we're essentially filtering out the oxygen from the air, venting the oxygen on site, and injecting into the pipeline the high purity nitrogen. So for the main pigging operation, we'd be at 95% purity. And for the final purge and pack, we can bring that up to 99% purity, still with the membrane generated nitrogen rather than any liquid nitrogen on site. And then in this instance, we've got 500 cubes of MEG storage and MEG injection pumps. So when the pigs are in the pig launcher shown in the bottom left there, we're then inject the MEG between the pigs and launch them down the line with the membrane generated nitrogen. So we balance a number of the factors there, and the solution is always just a balanced optimization and compromise of the competing factors. For the pigs themselves we have in the line are typically Baker Hughes designed and built as well. The cleaning and gauging pig shown on the left, so that's got wheels for support and to help it rotate as it goes down the pipeline. It carries the gauge plate for the internal bore, has magnets for picking up metallic debris. And we also do, the second image from the left is a wear test where we have the polyurethane sample being rubbed against a typical section of the pipe, where we do hundreds of kilometers, hundreds of hours of wear testing to make sure our blend of polyurethane is going to last the distance for the pigging operation. And then the caliper pig we also have in there, if required, to do the dent and ovality survey. Again, a Baker Hughes in-house item. The receive site, again, a much reduced footprint. So where we reduce the footprint of equipment also means far fewer people required. So the key parts of the equipment are the matching pig receiver to match the launcher that we had at the other end. Then a key bit of equipment is the high flow but low volume, so very low decibel at high flow silencer. So we blow all the nitrogen and air out as we receive. The separator separates out the liquid MEG from the nitrogen, so vent the nitrogen and collect the MEG. And then we collect the MEG and try to recycle as much as we can. So it tends to come out quite pure. So we remove the debris and send that MEG away for recycling. So the acceptance criteria that we're looking for there are so one, that it's a low mass of debris received. So we want, as part of the DNV waiver, the construction phase is very clean, is very well managed. There is low debris. But what we want to see when we're commissioning the line, pre-commissioning the line, is one, that mass of debris recovered in the MEG and on the pigs is low. But secondly, that it's of a decreasing trend. So we get less and less out as we work our way through the pig train. So when we get to the end of the pig train, effectively there's no debris being removed. We want a high volume of MEG to be removed, so we're not leaving MEG behind. So the integrity of that pig train and the speed control of that pig train is what we're trying to engineer for. We want high purity MEG at receipt, so very little water content, which tells us we've swabbed the line correctly. The high nitrogen purity at 95 to 99%. And then the intact inspection tool data and the gauge plate data to tell us that that bore is there as expected. So a reduced amount of equipment, but still there's quite a lot going on with this unconventional pigging train coming in and being received. So by way of conclusion, this technique, it's still in its infancy. So we've certainly done one very high profile project where it's worked. We've seen a lot of bids and tenders come in where it's either the preferred methodology or certainly one of the preferred methodologies being proposed. So there's a high burden of engineering at the early stages to make sure that the pipeline in question, as we see this developing through the industry, the pipeline in question maps onto this style of pre-commissioning, that it can be done. So a lot of engineering up front, but we can do this safely, we can do this economically. And it's not suited to all pipelines. The shorter pipelines where the hydrotest is still easy to do, where it's still cheap to do, or where we have jumpers or tees tying in, then we would still hydrotest. So this isn't the end of hydrotesting. It's just another technique that Baker Hughes are seeing increasing throughout the years. So the engineering tools mentioned, the flow assurance, CFD, computational fluid dynamics, and lab testing. With all these tools, we still require an experienced and well-versed engineering team to pick their way through the engineering data and come up with a sound basis for the pre-commissioning strategy. So there's still judgment calls within there, and still a lot of people's knowledge required to pull this off. So it is something we see going ahead in the future around the world. A lot of people are looking at this, and it's something that Baker Hughes are invested in developing this technique over probably the next decade. So we have a template for these kind of projects going forward. So it's to me, it's an interesting, exciting development, and I'd be happy to hear any of your questions regarding how we do this in the future. So thank you for your time, and we'll speak to you soon.
Hi, Peter. Welcome to the Virtual Pipeline Summit. Thank you very much for the presentation.
Hi, Danny. My pleasure.
I'd certainly encourage questions from the audience at this point, and we have already had some in. So let's kick off straight away. We've had one from Dominique Popinot from Total Energies. And the question is about the need for freshwater batch to remove salt from the hydrotest. But I guess the point here, Peter, is that you're not doing a hydrotest at all during dry pre-commissioning.
Yes. So with the way we're doing it in the presentation there, the dry pre-commissioning, there's no pre-flood, there's no full line volume of seawater going in. So the only water in there should be from the construction phase, where there's an amount of atmospheric, if it was raining, which it will have been at some point during the pipe lay offshore, or an small amount of seawater getting in there during the lay. But it's then very small volumes of water we're dealing with for that MEG swabbing. So the MEG volumes in there were partly to swab the moisture, but probably more to pick up the debris and lubricate the pigs. But I guess in the conventional hydrotest phase, where it is a line volume of seawater we're pulling out, as to Dominique's question, we can do a blend. You can try and desalinate fully with a potable water slug, a freshwater slug, and then MEG swab behind that. But you can also use the MEG slug to do the same thing. It will desalinate as it goes as well. So which is more economical or more efficient will vary pipeline by pipeline, but you can certainly, and we certainly have, used the MEG volumes to contribute towards the desalination process as well as the dehydration process. So it does work both ways.
Great, thanks for the comprehensive answer. I think that that catches it nicely. And yeah, you mentioned it depends from pipeline to pipeline. You showed the example there where 54 days were saved, which is phenomenal. You know, right before the pipeline starts to become profitable. There's always a lot of attention on the pre-com phase, right? Yeah. So where's the threshold between what makes the dry pre-commissioning advantageous?
As I said in the presentation, it will lend itself towards the export pipelines, a very high volume line, because there comes a point where the volume of the line is so large that the hydrotest is effectively almost rendered obsolete, because the ability to detect a leak on a high volume pipeline just by measuring the pressure at either end, you could end up being there for possibly a week taking your measurements, and you wouldn't be able to necessarily tell the difference between a leak and a small temperature change in a line that size. So I'd say certainly once we're going 32 inch and above, and probably 500 kilometers and above, I don't think the hydrotest will be making a reappearance. I guess from the Baker Hughes point of view, it's much easier, but each constructor will have to look at their own threshold for what they need to do to meet the DNV waiver. So it sounds very enticing to say we can remove the pre-commissioning step of a hydrotest, but there then are extra hurdles in place about your mill test, about your documentation and your welding procedure that would add additional economic hurdles once removing the pre-com, but it won't necessarily make it cheaper if those hurdles become too high. So certainly a large bore export pipeline is one where this would be a favourable solution.
Yeah, that's clear. And you did mention the more rigorous storage and control of the pipe sections at the start of your presentation. I guess, is that aided by the improvements and advances we're seeing in tech and big data, where you can, track the life cycle of a pipe section?
Yes, so I mean, as they come out of the mill and they get, so the cleanliness will be assessed at the mill, as is the strength test done at the mill. The caps will then go on each individual pipe spool, and they'll have their own RFID tag on them. So the life of that spool from factory to installation, it is tracked every step along the way. So the history of it is known, where they've been stored, how long they've been stored, and under what conditions, when they were welded into place. So the ability to have that comprehensive, so not just a 3D map of where the pipeline is physically, but the 4D map where it's been historically, as each of those sections of pipe is moved. The ability to control that process in a way that you can then demonstrate it to a third party like DNV, that control has been maintained from start to finish, is probably something that's fairly new in the industry. And it was then previously easier just to do a hydrotest at the end, because then that replaced a lot of documentation on the way. Whereas if you can produce that documentation from the start and deliver it at the end, that's what lends the flexibility to the process to say we can do this another way. We don't have to do it the way we've done it for 20, 30, 40 years.
Great. And perhaps less of interest to this audience at an offshore themed event, but perhaps this is also quite relevant for those areas where water's a scarce resource?
Yes, so we have done that in regions either where there just genuinely is no water, or there's a high risk of that water freezing when it was in the pipeline. So you end up with a lot of antifreeze in there, which would lead you towards doing a pneumatic strength test. So we can ditch the water, but then just do it on air or nitrogen. But that introduces a whole pile of other delicate issues as you navigate a high volume and high pressure test on air or nitrogen. So to be able to do it onshore, certainly in certain geographies, would have that appeal as well, for slightly different reasons. But yeah, I would agree. You're right there that it's the management of that water and the usefulness of the hydrotest in any circumstance that would push people towards looking into this kind of technique.
Great, thanks. And you mentioned safety there. That brings us to a good question we've had from Ahmed Kariri Abdul Ghani from the Malaysian Institute of Risk and Resilience. So he's asking what risk factors are involved with respect to dry pre-commissioning, and also how do you ensure the pipeline is clean after the construction?
Yes, so the risk factors. So one of the things I touched on in the presentation is, so there's a lot less risk in terms of we're not doing high volumes of water. We haven't got high pressure water. But one of the biggest risks we had was when we use the monoethylene glycol pipe swabs. So we're cleaning the line. So that's predominantly what we're using to clean the line. So we have the fluid swabs picking up debris in the line. But we also have magnets on the pigs. So the pigs are cleaning as they go, and they're picking up metallic debris on their magnets as they go. But most of the debris will be pushed out in solution in the monoethylene glycol. So it's acting as a dehydrator. It's acting for debris pickup as well. But probably the biggest risk that we had to navigate there was the risk of MEG and air being in a mixture together. because as we now know in the industry, MEG, when it mists, can be a flammable vapor, essentially. So within a pipeline, if you've got high velocities, you can have debris causing a spark. You can have static electricity causing a spark, or even the heat of compression if the flow stops suddenly or changes direction suddenly. So making sure the environment for the entire pigging operation was inert using membrane nitrogen was a key part of this. Because when we first started looking at this, there was the feeling that as long as the pigs were in nitrogen, then that was okay. You could run the rest in air. But it's actually then the venting down of the pipeline, when you vent it back down to atmospheric pressure, where you still have residual MEG vapor in the line, that you need to still have your nitrogen cover. So the biggest risk, the biggest headache and biggest risk is making sure you have an inert environment in that pipeline for running the pigs and running the MEG.
Yeah, comprehensive answer. And just on that, you mentioned the slug of nitrogen that you use. I've never heard slug in referring to a gas before. So what kind of volume or pipe length of nitrogen did you need to provide that safety blanket?
Yeah, so it varies region by region. In America, they still call a gas one a slug. Some other people call it a batch, but the key nitrogen batches we had in there was the first one ahead of the first batch of MEG. So we air packed the line, and then we had about 20 kilometers of nitrogen ahead of the first injection of MEG. And then we go to MEG, then we go to the pigs. And then the next batch of nitrogen in there was to separate out the two main fluid components of the pig train. So we had a first cleaning part of the train and a 50-kilometer nitrogen gap, and then the second part of that. And the purpose of that middle nitrogen batch or nitrogen slug is to separate out the mass of the MEG as the transitions along the pipeline profile, so you don't have too much MEG on either a downslope or an upslope at the same time, because the mass of the MEG will tend to accelerate downhill or slow it down unduly going uphill. So you're trying to control the pig train in the middle of what can be a very long line with two huge nitrogen or air springs at either end of that pig train. So trying to mitigate the speed excursions of the line with very limited resources. You can vent and you can inject, but beyond that, you have to balance your MEG masses as it goes up and down the hills along the line.
Certainly sounds like a challenging job, but I guess there's a good risk-reward curve there.
Yeah, there is, and I think it took a lot of digging to find that balance. I think some of the things that we intuitively knew or thought we knew when we started the process were overturned as we went through it. Some of the preconceptions about how this would work is actually the flow assurance simulations that twigged that there was a better way to do this and a more efficient way to do it. And it was a good team effort, I think, between Baker Hughes and our clients and subcontractors to come to a solution that was going to suit all parties.
Great. We like collaborative solutions. Just one question more before we wrap up there, Peter. It's from Joshua Stasik at EnviroTrace. He's asking about the testing pressures, I guess, at the pipe mill, right, compared to a standard hydrotest.
So for the way that we're using it, so the main reason we're doing it is to get rid of the hydrotest. So one, it's to do with the volumes of water, and two, it's to do with when it's installed, the pipeline becomes effectively unhydrotestable by design. So the way it would be designed if we knew we're going to hydrotest it versus when we know we're not going to hydrotest it, due to essentially the lateral buckling of the pipeline, that if it was to be hydrotested in situ, it would need to be trenched, it would need to be restrained so that the lateral buckling was taken care of. So I believe when it is just the individual spools, the hydrotest pressure will be lower, because we're then not doing the full integrity test at the end of that. So Baker Hughes wasn't actually involved in that scope, so I don't know by what factor it was lower, but I believe it would have been lower than the full hydrotest at the end had we done it that way.
Okay, great. Well, Peter, thank you again for a great presentation and excellent Q&A session.
No, my pleasure. Good to talk to you, Danny, and happy to have the questions.
Thanks, Peter.